Welcome back. So we were talking about second order guarantees, and we basically came up with a definition that excludes local maxima and simple saddle points. And we basically talk about the intuitive expectation that we need some requirement on the Hessian of the function in order to find these kind of solutions. Okay. And in this part of the lecture, we're going to talk about two algorithmic ideas. One of them explicitly leverages some information about the Hessian in the algorithm. The other one, on the other hand, just talks about or leverages intentional noise injection to avoid saddle points. But both of them require some regularity condition on the Hessian of the function in order to establish theoretical guarantees on the convergence of the algorithm. So let's start with the first idea. And this idea is sort of an elegant modification to the famous Newton algorithm. Okay? So Newton algorithm that you may have seen from your other courses is a general method, a celebrated algorithm for calculating zeros of functions. Okay? So in particular, let's say that I'm interested in finding x star that is the zero to this nonlinear function f. Newton algorithm says that perform this iterative update. So go from xt to the xt plus 1 by applying this update. So subtract minus function value divided by the derivative of the function and xt from your Collins solution to get the update. So this applies to any problem. So any f, whether it is again in this case it's a one-dimensional, but it also applies to cases where the function is multidimensional. Okay. In particular, there is a very direct implication for optimization. Let's say that you are interested in finding zeros of gradient of a function. Okay. So this is what we are looking for. Then we can apply the Newton method exactly as I've written here. So you go from the current solution to the next one by following the Newton update. In this case, you need the inverse of the derivative of the gradient. So that is precisely the inverse of Hessian times the gradient. Okay. So ht is basically the Hessian of the function, the second order derivative at wt. This is a shorthand notation that I'm going to use for the rest of the lecture. Now, therefore, as you can see here, Newton algorithm is designed to find first order solutions. Okay. Now, there are many variations of this elegant idea. I've listed a couple here. It's not again our major focus, but just for your interest. So we can have like the damp Newton method, where basically we may also include some learning rate here to better adapt the optimization algorithm to the landscape of the function, let's say. There is a Levenberg-Marquardt regularization idea, which basically replaces the inverse of a Hessian with what I've written here, which can be approximated with this expression. So the main idea is that in certain points during the optimization process, the Hessian may not be well conditioned. So that means that either the inverse does not exist, or if it exists, it's going to be a very, very large number. Okay. So by this kind of regularization, we're going to ensure that the inverse always exists and is well conditioned. So we are adding this regularization term to the Hessian and then take the inverse. Okay. All right. So and what's the connection to gradient descent that we've talked about before in the class? So well, the connection is quite simple. So if I replace the inverse of the Hessian with, let's say, learning rate times the identity matrix, I'm going to get exactly the update rule for gradient descent. Okay. So therefore, what this method is doing is kind of improving the local landscape condition of the function by leveraging a preconditioning matrix. Okay. So in particular, the matrix we are using in the Newton method is the inverse of the Hessian. The conditioning matrix that we are using in the LMR approach is this. And in general, you can have or design any conditioning matrix or preconditioning matrix that could lead to faster optimization algorithm and efficient updates. Okay. So this is the Newton method, but it turns out that this is not what we're gonna end up using to calculate second-order solutions. Okay. And to kind of motivate this and motivate the elegant modification to Newton method that I talk about, let's go back to the concept of majorization minimization meta algorithm that we talked about early on in the course when we motivated gradient descent. Okay, so what we said back then was that gradient descent is actually an example of majorization minimization for functions that are L-smooth, meaning that the gradient is L-Lipschitz, as long as the learning rate that you use in a specific iteration is less than or equal to 1 over L. Okay. So in particular, we showed that the update of gradient descent is equivalent to this basically equation 6, this optimization problem. Okay. So, and what we are doing, we are basically forming a quadratic upper bound on the function iteratively and minimize that to find our update rule. And given that the function is L-smooth, this quadratic function will indeed be an upper bound of the function. Therefore, gradient descent becomes an instance of majorization minimization. Right. So can we make a similar claim for the Newton method? And the idea is that no, that's not necessarily true. Okay. We can, in fact, show that the Newton update is equivalent to minimizing another quadratic function, the one that basically leverages the Hessian. Okay, so we can very easily show that the solution to this optimization problem that I've written here is going to be the Newton method when the function is convex. Okay. Such that the Hessian exists. On the other hand, it may not necessarily be true. Okay, so because depending on the Hessian, this quadratic function could be convex or non-convex. All right. So therefore, basically the Newton is the Newton update can be derived from this equation by simply taking the gradient and setting that equal to 0. Okay. However, there is a major difference between doing that for equation 7 and equation 6. Equation 6 is a convex quadratic function, so taking the gradient equal to 0 will give us the optimal solution. Equation 7, on the other hand, will only give us the optimal solution when the Hessian is positive definite. Okay. All right, so that's basically one difference between these two ideas. Okay, another difference is that we are not necessarily minimizing an upper bound on the function. Okay, so I can give you quite a few examples. For instance, I can give you an L-smooth function where this term is actually less than L times the norm square of W minus WT. What does that mean? It means that whatever I am minimizing locally at time t is not an upper bound on the function. So therefore, Newton is not necessarily an instance of majorization minimization paradigm. So it means that we may not necessarily benefit from the benefits of the majorization minimization. Okay, and because of this reason, Newton method is not going to be sort of helpful when it comes to avoiding saddle point. Intuitively, what is happening is that, again, Newton method is designed to solve first order stationary conditions. So this is by design, we are trying to find a point at which the gradient is 0. We are not necessarily and actively trying to avoid simple saddle points. Okay. In particular, we are not finding a point at which the gradient is 0 such that the Hessian is positive semi-definite in order to find a second order solution. Okay. Right. So what's the idea then? The idea is to sort of try to come up with a natural extension of gradient descent that is going to be an instance of majorization minimization for functions that have Lipschitz Hessian, okay, as opposed to the Lipschitz of the gradient. So once we come up with this natural extension, then we have an instance of majorization minimization algorithm. We can use that to find second order solution. So, and again, the idea is that gradient descent is the most intuitive idea to find first order solution, and it is an instance of majorization minimization. We're going to find its intuitive extension to the second order case. Therefore, we'll be able to find basically second order solutions. Right. So I've been so to talk about this algorithm, we kind of need to talk about a little bit more precisely about the notion of Lipschitzness of the Hessian. So that I've mentioned a few times so far. So let's go over the definition then. So we call a function rho second order smooth when the Hessian is Lipschitz. In particular, the norm of the difference of Hessian at two different points, W1 and W2, is bounded by some constant rho times the difference of W1 and W2. Okay. So one side note about these norms. So here we are talking about the Euclidean norm, but the L2 norm of a matrix is basically is talking about the maximum eigenvalue of the matrix, as long as our matrix is symmetric, okay, which Hessian is. So this basically means we are talking about the maximum eigenvalue of the matrix as a result of the difference of Hessian at W1 and the Hessian at W2. Okay. All right. So this is basically the definition of second order smoothness or Hessian Lipschitzness. And it turns out that this is equivalent to these two conditions that I'm writing here. Okay. So first condition is basically saying that there is a cubic upper bound on the function, okay? And second condition here is saying that the gradient is smooth, okay? Basically means that the gradient has a quadratic upper bound and a quadratic lower bound, okay? All right, so now how can we use this idea? Again, let's go back to what we did for gradient descent. For gradient descent, we said that thanks to first order smoothness, we have a local upper bound on the function. Turns out to be a quadratic upper bound. So let's minimize that iteratively. Now, in this case, where we have second order smoothness, we have a cubic upper bound on the function locally. So what's our idea? The idea is to minimize this cubic upper bound iteratively, okay? And this is exactly what we're going to do. And this gives rise to this elegant algorithmic idea, which is called the cubic regularization of the Newton method. It's called the cubic regularization because these terms that I've written here are exactly the terms we had for the Newton algorithm, but we are regularizing that by including this cubic term. So that's why we get the cubic regularization of the Newton method. And interestingly, this update, although it looks very, very complicated, it can be shown to be equivalent to a convex optimization problem when we have a problem in multiple dimensions, notably when the dimension is at least 2. All right. So this is basically the first method that I mentioned, right? So it's a method that explicitly leverages Hessian information in the update to make sure we can avoid simple saddle points as well as local maxima, and therefore converge to second order stationary points. Okay. So what's the main idea behind this algorithm? Okay. So first of all, because we are imposing that the Hessian is rho Lipschitz, the method is going to become an instance of majorization minimization. So is going to be a descent algorithm. We are continuously reducing the function value. So we are satisfying the descent property, something that we may not necessarily satisfy if we use the Newton algorithm. Okay. So that's basically one benefit. Another benefit, or rather another idea to see how this cubic regularization of Newton method works is to consider the spectral decomposition of Hessian. Okay? So what does this mean? It basically means that we have an eigenvalue decomposition. For any symmetric matrix like Hessian, we can write it down as basically sum of eigenvalues times the sort of the product, the outer product of the eigenvector itself. So basically, we're talking about the U transpose. Again, lambda I is the highest eigenvalue. Could be negative, could be positive. It is real because the Hessian is symmetric. Ui is basically the eigenvector. Okay. Right. Now let's consider this, and let's use this in the update of the cubic regularization of Newton method to arrive at this equivalent update. Okay, so we are updating W in this specific way by minimizing again a cubic upper bound on the function. So this term is constant; it doesn't matter. So this is a linear term like we had before. Okay, this is the cubic regularization term, and I want to draw your attention to this term. Okay, so previously this was basically W minus WT transpose Hessian W minus WT, and then by using the spectral decomposition of the Hessian, I can write that equivalently in this form. Okay. Now let's see what is happening. Okay. So here I have a term. So this is basically positive. Okay. So it's a quadratic term. The whole thing is positive. The eigenvalues, on the other hand, could be negative or positive. If an eigenvalue is negative, that means that if I move along the direction of the corresponding eigenvector, I'm going to sort of reduce the function. And if the eigenvalue is positive, it means that if I move along the direction of the corresponding eigenvector, I'm going to increase the function value. Okay? So therefore, we are kind of penalizing, by using this update, we are penalizing directions along UI with positive eigenvalues, okay? Because those are the terms that will appear here with a positive sign. Because we are minimizing, we're going to penalize them. We're going to make sure that our update is such that we don't move along that specific direction. Okay. On the other hand, by following this update, we're going to take advantage of directions with negative eigenvalue. Okay. The idea is that those terms will have a negative sign. We are minimizing. So if I move in that direction, I can theoretically minimize the objective function of this optimization problem to even minus infinity, let's say. Okay. So therefore, the main idea is that by using updates like this, by using the information provided by the Hessian, we can take advantage of the negative directions to make sure we are increasing the function value, and we can take advantage of the positive or we can penalize the positive directions to make sure that basically we converge to a good solution. Now, what I mentioned here does not care if the gradient at that point is 0 or not. Okay, so let's say the gradient is 0. So this term will be 0, doesn't contribute. On the other hand, this term that depends on the Hessian is still active. So if I have a simple saddle point, for instance, where all directions are positive, one of them is negative, conceptually, I can take advantage of that specific negative direction to minimize the function value and therefore avoid the saddle point. Okay. So this is basically the main idea behind this algorithm. Look at the Hessian, penalize directions that increase the function value, take advantage of the directions that reduce the function value. Okay. And very crucially, we can actually show that this method can indeed find a second order solution with this many number of iterations. Okay, not only we can find a solution at which the gradient is very small, but also we can find a solution at which the minimum eigenvalue of the Hessian is not too negative. That basically means that the solution we find is not a local maximum and is not a simple saddle point. And in a lot of problems across machine learning and deep learning that are non-convex, that could be basically a local minimum. All right. So the proof is a little bit involved, but I just want to mention the main ideas, okay, to see how we can establish this result, okay. So the first step is that is as follows: that if there exists a direction with sufficiently large and negative eigenvalue, essentially a direction that I can leverage to minimize the function, then we can indeed identify that that direction and leverage it to reduce the function value. Okay. And crucially, the point I want to make here is that the amount of progress we are making depends on how large that negative eigenvalue is. The larger it is, the more progress we are making. Also, it depends on the condition of the function, in particular the Lipschitz constant of the Hessian. So the better condition the Hessian, meaning that the smaller the rho is, the more progress we are making. And this is sort of a natural analogous of what we talked about before in the context of gradient descent and finding first order solution. In the proof of gradient descent in particular, we established a bound on the amount of progress we are making. And the bound was basically proportional to the gradient norm. The larger the gradient norm, the more progress we're making. So now this is replaced with lambda. And it also was inversely proportional to the Lipschitz constant of the gradient. The better condition the function is, meaning the smaller L, the more progress we are making. And now in this case, this is replaced with rho. Okay. All right. So therefore, the first step is, if there is a significantly negative eigenvalue, we can identify that direction and leverage it to make progress. Okay. Otherwise, there are two cases. So otherwise means that if we are at the point at which all the eigenvalues are very, very close, are not too negative, basically. So in particular, it means that we are satisfying one of the conditions of the second order stationarity definition. Then two cases appears. Okay. So first of all, if the norm of the update is small, then it turns out that the gradient norm is also small. So it means that not only we satisfy the condition on the minimum eigenvalue, but also we satisfy the condition on the gradient norm. So it means that therefore we have found a solution. On the other hand, if the norm of the update is not small, then what we can show is that we can still make progress. So if the norm of the update is not small, we have not converged yet, and we can still make progress, such that crucially, the amount of progress that we are making is strictly less than some, let's say, some negative number. So the most important point here is this strict inequality, which we can then leverage in the last step to use an idea based on contradiction to show that we can find a solution precisely after these many iterations. Okay, so that's basically the main idea behind the proof of our first algorithmic idea, cubic regularization of the Newton method. Again, the algorithm leverages information about the Hessian explicitly in the update of our parameter, and also it leverages regularity condition on the Hessian in the theoretical analysis. In the next part of this lecture, we're going to talk about another algorithmic idea, which only leverages regularity condition on the Hessian in the theoretical analysis, and uses a different idea, notably noise injection in the update. So in some sense, it's more efficient than the algorithm we talked about here. I'll see you in the next lecture.